In this video, I will identify factors that influence the velocity of action potential conduction and define saltatory conduction. The action potential is an all-or-nothing response generated at the axon hillock that will spread down the axon to the axon terminals. So the magnitude of an action potential is a constant with a rapid depolarization during the rising phase from the resting membrane potential of -70 to a positive value around positive 30 millivolts. Then repolarization occurs during the falling phase to bring the membrane potential back down to resting potential, and then hyperpolarize for a brief period, about a millisecond, before returning to resting membrane potential. The entire duration of the action potential at any one location of the axon lasts about 2 milliseconds. However, the velocity of action potential conduction, that is, how fast the action potential spreads from one point in the axon to another point in the axon, is not constant. There are a number of variables that can influence how rapidly an action potential can spread down the axon. Action potentials typically travel in the range of about a half a meter per second up to around 120 meters per second. This graph shows us the relationship between axon diameter and action potential conduction velocity. You can see here that larger diameter axons conduct action potentials with a higher velocity. And this relationship can be described with Ohm's law. Ohm's law is that the electric current, represented with the symbol I, equals the voltage divided by the electrical resistance. And the electrical resistance of an axon is proportional to its diameter. So a larger diameter axon will have less electrical resistance, meaning the action potential is able to spread more easily down the axon and moves, therefore, more quickly. That is, the current is a higher velocity of action potential spreading down the axon. So this illustration may help us to think about how diameter influences action potential conduction velocity. As an action potential is spreading down the axon, what's occurring is sodium ions are rushing down the axon, and those sodium ions have a positive charge. But as the sodium ions are moving through the axon, they could bounce off of molecules inside. They could bounce off organelles or proteins or other ions inside of the axon. But having a smaller diameter axon means that there is less space for the sodium ions to move around and make its way down the axon, whereas a larger diameter axon will have a larger amount of space. There will be less electrical resistance. And with less electrical resistance, the current, the electrical current, the speed of the flow of ions will be faster. Temperature also influences the rate of action potential conduction. We can see here that a increase in temperature between 29 and 38 degrees Celsius leads to a proportional increase in action potential conduction velocity. And this is because increasing temperature increases the kinetic energy of molecules, and the current, the flow of the action potential, results from the movement of sodium ions. As sodium ions are entering the cell by facilitated diffusion and then spreading through the axon to create the movement of the action potential. Increasing temperature increases the rate of that diffusion, increases the rate of movement of ions, and therefore the action potential can travel at a higher velocity. Myelination of axons can also increase the conduction velocity. Myelination is an insulating sheath around an axon that is produced by glial cells known as oligodendrocytes in the central nervous system and Schwann cells in the peripheral nervous system. This myelination prevents the movement of ions across the plasma membrane. There are spaces in between the myelin sheath known as the nodes of Ranvier. And the voltage-gated ion channels are concentrated there at the nodes of Ranvier, enabling the mechanism of saltatory conduction, where the action potential will jump from one node of Ranvier to the next node of Ranvier. The myelin at the internode spaces will increase the velocity of the action potential by preventing ions from leaking out of the axon. On the top here, we can see the mechanism of action potential conduction by saltatory spread, where the voltage-gated sodium channels are concentrated at the nodes of Ranvier, and there will be very little leaking of sodium out of the axon at the internodes. Therefore, the action potential will jump from one node of Ranvier to the next in this mechanism of saltatory conduction. In contrast, an unmyelinated axon will have a slower spread of the action potential as sodium ions enter through voltage-gated sodium channels and then are able to leak out of the axon as they're spreading through. So sodium ions are constantly leaking out of the axon, slowing down the rate at which depolarization spreads down the axon.